Perfect. So let's get started. Today we are going through the fundamentals of augmented reality. We will go through a little bit about the past, where are we coming from, and what is the current state, and then taking a look also into your future, that how augmented reality can be shaping whatever you will be doing professionally. So, brief introduction. I'm Sauli Kiviranta. I work today at Delta Signi Labs. I'm the co-founder and CTO, leading the product and engineering teams. My background is on electrical engineering. While I was doing my studies, I was heavily being involved in 3D modeling, level design for different modding communities on Battlefield and Counter-Strike. And this gave me a perspective on real-time 3D. So I ended up working at VTT, a virtual reality team called Human Machine Interaction and Virtual Engineering. And this was an interesting place where we were trying to solve industry problems by applying virtual and augmented reality. So it was a nice combination of real-time 3D applied to solve industry problems. And some of the projects were task design problems. How can we design machines and maintenance tasks by using virtual environments, as well as cabin design and interior design and 3D modeling challenges. We were working with Elomatic. I was setting up Elomatic virtual reality laboratory on Jyväskylä back the days, and as well as working with ITER thermonuclear fusion reactor, where we had to do a lot of maintenance and service task validation by using virtual models. Also, ergonomics was obviously, virtual reality is heavily involved with the human factors. So we were doing a lot of ergonomics studies and assembly cell design, for example, in this case, Momentus, and different maintenance techniques, how we could train maintenance techniques by using virtual reality. In this case, Technotom for the nuclear power plants, and then different simulations, that how we can use simulation results and visualize those results to the designers and engineers, for example, cabin design for mining loaders. So different kind of industry projects, and always the idea was that can we somehow bypass some real world constraints by using virtual and augmented reality technologies. And one of the projects was with the Thales Alenia Space for instructing astronauts remotely. We will come back to that at the later part of the presentation, from where the Delta Signi Labs was actually formed. So Delta Signi Labs is a VTT spin-off. We launched the company in 2013. Today we are 8 persons, and we are headquartered in Tampere, Finland. We have a daughter company in Germany, and 50 corporations and 50,000 users on our AR products. So for today's topic, it's important. I think this is by far the best characterization of virtual and augmented reality technologies. It comes from a pretty old movie, but I highly recommend it if you have not yet seen the movie. It's called Matrix, where Morpheus introduces the virtual reality and describes that you have to think that what is real. If it's what you feel, what you smell, and what you taste and see, then it's nothing but electrical signals coming into your brain. And when we look at the virtual reality from this perception side, we can start to see that, in fact, the visual aspect, what we classically define as virtual reality as how to visually represent the simulated environment is insufficient, and we should in fact look at all of the main senses what we have. And that will be our first part of this lecture. So we will look a little bit into our history and see that can we find some cues from our past that will be helping us in understanding what is augmented reality, why does it look like what it is today, and what will it be in the future. And this first part we will be dividing in 3 categories. We have 3 different modalities that we will go through. And the first modality is revolving around our perception of reality along those 5 sensory grooves, what was introduced so nicely by the Matrix movie. So sight, how we see, how we perceive the real world in visual sense, and then how could we simulate that sensory input, as well as hearing, what kind of aural cues we have from our surroundings, and how could we simulate those, as well as touch, smell, and taste. Those are usually not so dominant, but I just want to highlight them here, that we don't forget all of our senses. In many instances, we may actually benefit greatly from using other senses than visual or even aural. And I put here some pictures of other creatures that are dwelling this universe. And as visual creatures, as humans, we are visual creatures. So we tend to be thinking things in a visual way. And our solutions usually end up being revolving about visual feedback. And just if you look at the other creatures, if you think about, for example, bats, their perception of the real world is actually aural. So they don't so much see the world, but they hear the world. Or if you think about the butterfly standing on a flower, its perception of that flower is in terms of taste. A butterfly has a taste buds on its feet, so its understanding of the world is in this sense based on taste. So just to give a little bit of a twist on our own tendencies to categorize our understanding of the world with our senses and how they work, and especially the visual sense. So if we look back into our evolution and we look back 500 million years, we see that their living creatures as involved started to develop sensitivity to visible light. Vision starts to develop at about 500 billion years ago. And about 370 million years ago, we start to get sensitivity to pressure waves in the atmosphere. So audition starts to develop. And about 2 million years ago, we start to be able to produce pressure waves. And the first versions of what is called proto-language starts to develop. So it's not only our ability to perceive the world, but also produce pressure waves. And this would constitute a proto-language. And about 400,000 years ago, we have the visual acuity of the modern eye. How we today see the world is about 400,000 years old. So what does it mean? What does this first 500 million years of evolution actually signify? So it signifies that in our brains, our ability to perceive and understand the world, mainly in visual sense, but also in other ways, gave us an ability to, first of all, spatial reasoning, to be able to perceive the real world in 3D. And when we put all those sensory inputs into one, we would call it concrete reasoning. So let's say that we hear some sound coming from a tree or a bush, and we look to that direction. We see animal on that direction, and through our somatosensory system, our haptic perception, we are able to shoot an arrow, and our spatial and temporal understanding will allow us to shoot the arrow a little bit in the future, where we expect the animal to be impacting on the same trajectory. So this first 500 million years gave us ability for concrete reasoning, and the main aspect of this concrete reasoning is the visual side and what we would call spatial reasoning. Of course, oral and auditory system is also spatial, mostly in terms of direction, but to some extent you could say that auditory is also spatial. So we started to have a sense of relation, location, about motion, distances to object, proximity of different objects related to each other, sense of color, taste, and smell, and this was the first 500 million years of our evolution. So now we have covered the first modality, the concrete reasoning, and the spearhead of that, the spatial reasoning. And what is the second modality then? We have to go back to our timeline and take a look at what is happening next. So within the previous 100,000 years, we start to get an actual oral language. This is about the time when humankind was able to start producing meaningful oral cues and start forming words that signify some real world objects and even some primitive sentences. Then 37,000 years ago, we started to be able to count items. And this is a pattern that emerges from our ability to start attributing real world things with some oral cues. So we figured out that we can actually start signify groups of items by counting them. And then about 10,000 years ago, we started to be able to have numbers for the collections of items. proto-writing, so our ability to actually mark down those abstract notations of objects or collections of items and give them symbolic representations. And what we would say today, call it mathematics, manipulation of numbers, and written language like symbolic sequences of our verbal descriptions is only about 5,000 years old. So this 100,000 years of development we would call abstract reasoning. So now we are not so much concerned anymore directly about the real world objects. We are talking about our abstract representation in our minds of those real world objects. Is it symbolic that we model a real world object with a primitive drawing? Or is it even more abstract that we just say that this set of characters represent a thing in the real world? So that's about 100,000 years old. So now we start to have references, we start to have properties of objects, we can have syntax, grammar, denotations, and we can actually start to abstract the abstractions that we may have a chains of abstractions, and we start to get further and further away in our mental models from the real world objects that we were able to build the mental models on the first 500 million years. So that's the second modality. And before we jump to the third one, let's take a look at these first two modalities together. How do they look like? Again, back to the timeline. So about 500 years ago, a person, Italian scientist called Filippo Brunelleschi, invented linear perspective. So now, only for 500 years, we have been able to start create visual simulations of real world objects in fairly accurate way. So instead of having a very coarse model, a symbolic representation, now we were able to start producing visual renderings, if you will, of real world objects, spearheaded by Filippo Brunelleschi. He invented this technique, and then he wanted to prove to his colleague scientists and artists of the days that his technique is actually conforms to reality. So he devised this kind of a very interesting setup where he has a mirror and a painting that he has been using his linear perspective technique, and a hole in the painting and in the mirror, so that you can actually perceive the real world and align your painting on top of the real world through the mirror. So this interesting demonstration actually looks fairly similar to what we see today in augmented reality. When we take our tablet device, our nice iPad with AR kit, or Android device with AR core, and we try to align some 3D models on top of the real world, it was exactly the same visual concept what Brunelleschi had to do. Of course, it's not dynamic, but it's in essence, he had to do first instances of augmented reality 500 years ago to demonstrate to his colleagues that his technique is actually conforming how we perceive the reality in concrete way. So that's what Brunelleschi can be said, that he was the pioneer to some extent of augmented reality, that he had to devise this technical construct to simulate his to prove that his rendering technique conforms to how we perceive the reality. And the impact of that was pretty big. So everything what we see today in art ever since, and a very nice depth perception in those on those artistic pieces, as well as today we see similar kind of perspective tricks in street art, as well as our 3D engines, 3D modeling systems, our augmented reality systems, and head tracking and other ones that allow us to draw realistic pictures with our computers. So a lot of that is thanks to Brunelleschi's invention for visual simulation. If we go forward, so what happened 50 years ago? We started to have first optical constructs that allows us to tie graphical content into the real world. So this was first in fighter planes, that the optics for targeting were point of view free, that in fact it was irrelevant to a large extent where's the pilot's head, and he could look through the optics and see the target pointing at the right position on the sky where the machine gun was actually pointing. So parallax free view of graphics content was developed about 50 years ago. And then 1990, Thomas Caudell from Boeing coins the term of augmented reality, and he has this nice illustration of a 3D model of an airplane and instructions, graphical instructions digitally overlaid on top of those structures. And he called this augmented reality. But in fact, if we look at popular culture, already in 1984, in a movie Terminator, we saw some glimpses. We were not able to really yet give it a specific name, but we saw some examples of augmented reality. What we would today call augmented reality was when in Terminator movie we saw this abstract and concrete overlays on objects by the character of Arnold Schwarzenegger. So the concept itself was already in popular culture, and Thomas Caudell came and gave it a name. So far, what have we learned about these two categories? So Brunelleschi invented the perspective drawing technology, and this allowed us to unleash the power of spatial reasoning and do visual simulations for art and engineering. And we started to have augmented reality taking step-by-step shape. And this technology allows us to leverage those two ways how our mental models are constructed, the concrete reasoning side as well as the abstract reasoning. And here it's important to understand that these are two very distinct categories of understanding, and it spans across these 500 million years of our evolution from where these aspects come from. So let's take a few examples about our biological senses, and we start from the visual side. So how would it work if we tried to augment our visual field of view from the concrete reasoning point of view? Well, that's already what we saw in the pictures. For example, here on bottom left corner, you have a fairly interesting glass object placed on top of a visual marker. And in fact, in many cases, I could replace this glass object with a 3D object and use real-time 3D engineering rendering from Unreal or Unity 3D, and you would not be able to recognize that which of them is the real object and which of them is actually just a 3D rendering of a glass object. Well, in this case, the picture actually has a virtual object. This is not the real glass object. So this is when we are tapping into our concrete reasoning, and we are starting to put in AR. In VR, we are fully trying to simulate all our visual input, but on AR, where we are starting to place virtual object into the real world and utilize them for some engineering purposes or entertainment purposes. And on the right side, then we are more concerning about the abstract reasoning side. For example, we put abstract symbols and agree collectively as a society that this symbol denotes danger. So if you see this kind of a sign, abstract representation, let's say of a lightning, that's something that symbolically represents a lightning, people generally understand that it's probably not a good idea to touch that object. This would be, for example, in Google Glass, when you have a spatially aware software that understands that you're reaching a dangerous location, and it would show you an abstract symbol on the screen and say that, hey, we are entering a dangerous zone. So this would be abstract reasoning in terms of visual input. Then when we look at the aural augmentation, I would recommend if you're interested in aural augmentation and how to simulate spatial things in audio side, to take a look at the virtual barbershop in YouTube. Just take a headset and watch through that, or listen through that video, and you get a very interesting idea how you could use spatial audio to position things and augment your understanding of the real world with virtual aural cues. And on the abstract side, any kind of alarm, again, it's a matter of a societal agreement that this type of a sound denotes danger or pay attention, like a beeping truck, that, hey, be aware, there's a potential danger in this direction, look around, pay attention, don't get hit by the truck when the truck driver is not able to take care of that you are not there behind. So those would be abstract augmentations of the world in aural sense. Then we proceed to touch. On the concrete side, we have all the different kind of haptics when we are trying to simulate the haptic feeling of objects, of virtual objects. And why not just take an example from the toys of children? They are usually rough physical objects that simulate, for example, weapons or cars or other toys. And that would be a concrete augmentation of your real world in terms of sense of touch. And that we can also communicate. We have a few scientific examples of how to remotely communicate about concrete sites, but that we can take a look later. And on the abstract side, for example, this dimple writing for blind people is a very specific form of abstract communication through touch. That we don't need to necessarily always involve our eyes or our ears, but we can actually read through our fingertips. Not very common, but it's good to understand that we have this kind of ways to convey abstract information for the humans. It's just a feedback channel that we can utilize. And on the smell side, again, gets a little bit trickier when we go to this little bit unconventional ways of augmentation. So on the concrete side, you could imagine a toilet that is being augmented with the smell of flowers. So that's a concrete augmentation. You are trying to be put into a different place in terms of your smell sense, or even some computer games try to reinforce their simulations by adding a system that allows you to smell as if you were somewhere else. And that's on the concrete side. And on the abstract side, it's I found I think fairly interesting example of how to communicate abstract information through smell. Back the days when, especially in Europe, in France, when propane was introduced, it's a smellless or odorless gas and very dangerous. That if there's a propane leak, and you ignite a smoke or a candle in the room, it's a disaster. It's an explosion, and they had the problem that how can we communicate through this medium of propane that something is wrong. And the first attempt was that let's add a scent of vanilla into the propane. So we have a medium of gas and we try to communicate abstract information through the gas, and we try it with vanilla, with the smell of vanilla. But of course that's a little bit counterproductive because vanilla is actually a good smell. So it's like opposite effect what you would like to communicate, and people are rather enhanced by vanilla, and then they realized that okay, we need to have something very very sharp annoying smell, and that's where ethanethiol was introduced to propane. That when you smell this sharp, when you have this sharp smell, you immediately recognize that okay, there's a leak somewhere, that this is a problem, and that way you can, even through smell, you can communicate abstract information that hey, there's a danger around, pay attention, be aware, react to the danger in just the smell sense. And on the taste side, obviously all the products on the market that try to simulate artificial tastes in candies and in soda, that's a concrete augmentation to manipulate your taste senses. And in the same sense what we had in the smell, in the prohibition time, there was a problem of taxing of alcohol, and first solution to communicate to the people that this alcohol has not been taxed, it's an industrial alcohol, was to add poison into the alcohol. So you're trying to abstractly communicate through the medium of liquid message that this alcohol you shouldn't consume because it's not taxed, and people started to die. So it was not very good way to communicate information, and that's where we got denaturated alcohol, that it's just extremely nasty and causes vomiting to some people. And this is an abstract way to communicate that this alcohol is not for your consumption. It's an industrial product, and you should not be consuming. So communicating abstract information through augmenting of taste. So now we have gone through the first two modalities, and we have the third modality left. Let's take a look what is going on here. If you look at the human senses, our ability to observe the environment and collect information from the environment is fairly limited. This is just what the evolution has given us throughout those 500 million years. How did we have to survive? What was optimal for us to survive the real world as it is? We have these five main senses. But in the advent of technology, we have developed massive array of different ways how we can actually observe the world and sense things in the real world, and build better and better understandings beyond those biological senses. So the third category is transformational reasoning, that how can we take our technological means and transform those observations from those sensors into the five senses, so that as human beings we can understand how the real world works. Let's take an example of infrared camera. This is transformational reasoning. We use a sensor that can observe the real world in the wavelengths of infrared that our eyes are not capable of observing, and we transform those observations into the visible wavelengths that we can observe. So that's a form of transformational reasoning, that we take a phenomenon in the real world and transform it into something that we as a human beings can observe. And this doesn't necessarily mean one-to-one mapping. You may transform a phenomena that is on optical wavelengths, and you can transform it, for example, to touch sensation, if in the use case this is more meaningful. You don't have a sensory overload. So be completely open in engineering sense, that how do you want to do transformational reasoning. So that's our three modalities. Why augmented reality exists, where did it come from, and why do we have such a concept now, what we call virtual reality and augmented reality. Let's take a look at, like, if we were to try combine these three things and take some example scenarios and see what would be happening if we try to take these technological observations and transform them to our senses. So here's an example of augmented reality helmet for a fireman, or for any kind of a safety worker. Let's use a Fukushima example for the radioactivity, that you could have a sensor in your helmet that is able to observe the real world in terms of temperatures or even radiation, and then you would transform. It may be even coming through some other bigger sensory systems, but you just visualize the heat map to the firefighter, that hey, here these blue corridors are the areas where you can still walk and spend few minutes without getting radiation poisoning, and these red areas are such that you cannot enter. So this would be taking a sensor measurements or observation from the world and transforming it into the firefighter, and help them navigate or avoid dangerous spots. For example, with infrared camera, that there's definitely fire behind the door, so don't go there. Other example would be, for example, from Mirka, when using polishing products on cars, it's very hard to observe that what is actually going on with the surfaces, and you have to be very skilled operator to do it well without causing damages to the paint. And here we just take an infrared camera like FLIR and map that view into the headset of the user, that they can actually perceive the surfaces in infrared and recognize if some surface is reaching too high temperature for their use case. And here's one very wild example, just to demonstrate the power of transformation and transformational reasoning. We have an example of Lance Corporal Craig Lundberg, who was unfortunate enough to lose his eyesight in combat. And what the scientists did, they put the camera on his frame of his glasses, and this visual array of pixels is actually transformed into an electrical signals in his taste. So what we talked about, these butterflies, taste buds on the feet, how a catfish is actually tasting how the water feels in the ocean, how the dog, for example, is observing the world in the smell, rather than visual impact. Lance Corporal Craig Lundberg is able to taste how the world looks like. And this is a very, very interesting like example of how plastic and how malleable and flexible our brain actually is. He is able to see the world through taste. Another example, this is more speculative. Let's say that we wanted to improve Kimi Räikkönen or any of these rally drivers, formula drivers' perception of the slipperiness of the road. We could install some strain gauges on the wheels and put a haptic actuator on his gloves. And while he's driving in the curves, he would be able to feel on his fingertips how the machine is actually feeling the road. And you could drive much faster and avoid dangers when you have this kind of a haptic sensation, or how does the road feel like. And there are some examples from people who have been paralyzed that have been installed on a wheelchair, that actually the brain itself doesn't really care if it's a living limb or a living tissue that you have. The brain itself subconsciously accepts the machine as an extension of the body. So it's nothing about your consciousness, it's your subconsciousness and your brain's ability to perceive what is you and what is the machine part. And it turns out that the brain doesn't actually care how do you augment and extend your perception of the real world. So what did we learn about this augmented reality so far? So we went through the concrete reasoning and abstract reasoning, and now we went through a few examples of transformational reasoning and even touching a bit of the use cases, that how these new senses could be mapped into our ability to understand the world. And it's important to remember that our brain is extremely plastic, and don't be afraid. The brain will adapt. It's more about your ingenuity and creativity to find these transformations and enhance the human abilities through augmented reality. So I come from the school of human machine systems. It's a specific school. If we think about engineering or even human factors, it's there exactly in between engineering and human factors. Human machine systems school is the one who says that let's focus on the goal. What is the system that we need to achieve our goals, and combine the best abilities of human with the best abilities of machine, technology and society, put them together in unity, and that way we can reach our goals more effective, faster and better. So that's the school of human machine systems. So to kind of conclude this first part, I would say that we have not even started to properly leverage the human potential. So now we start to have all the ingredients, technological ingredients, and our understanding of the humans and the technological side, that we can actually start to truly augment the human capabilities. And AR is one of the core technologies that will help us in doing that. So to recap, the purpose of augmented reality is in augmenting the human capabilities in unity with the best of technologies. So this way we can go beyond our biological limitations, whatever evolution has given us. Now we can start going beyond that point, and remembering that we have to always have a clear idea of the goal. We don't do technological augmentations for the sake of its fanciness. We have to have a clear understanding what is our goal, what is our use case, why do we want to enhance the perception of the human with this technology to better achieve the goals. And I can share the link later. We have an article on very much this topic on unity of human and machine. And it could be interesting read for some of the students. So that's the three modalities on why augmented reality exist. So part one is done. We have found some cues from our past that why today is what it is and why the future will look along those lines. So now we can take a look. Now we have taken this historical perspective, and we have a little bit better understanding of the background of things. And I feel that it's extremely important for us to have this evolutionary and historical perspective, so that we don't get emotionally and mentally so attached to the technology, that we can look at the technology just as a way to implement, achieve a goal. That if we need visual augmentation, okay, let's see what kind of displays we have available. Okay, if we need some aural, so that's why I think that the part one was important to go through first, and now we can take a look like more classically, what do we see on the market in terms of augmented reality? What kind of devices there are? Of course, they are mostly visually dominant, as we now understand, but at least to get an idea what is out there. So there are three main pillars in augmented reality, and it's pretty much exactly the same for virtual reality. So we have the tracking systems, and the purpose of tracking systems is to answer the spatial question that where is the observer, and where are the things, the virtual things or the real things that are of our concern in this specific use case. Then we have the display devices that conform to our this visual dominance of human beings, and those devices answer the question that how do we observe the augmentations in visual way. And then the content is actually the implementation of the use case, that what do we want to augment, what do we want to visualize in a specific location, what is the use case, what is the added value that what we try to bring to the human being, or what is the goal that we are trying to achieve. But first, let's go through the tracking systems and take a little bit closer look what is going on with the tracking systems. So in terms of tracking, it's very important to ask yourself a question when you have a specific use case, that, okay, what is the scale of spatial awareness that is relevant for my use case? That is it on the observer side, is it important where the user is looking at? Are we doing eye tracking? Is anything else important at all except the exact trajectory where the user is gazing? Or is this too accurate information? Do we need very sophisticated eye tracking technology to understand where exactly the user is looking at, or should we do head tracking? Is this enough? The position and orientation of the user's head in terms of the virtual content, or do we have to go to the larger scales, to the body tracking, or even location tracking? So this is important question to ask yourself, that you don't kind of mix different concepts when you're trying to solve a specific problem. So when we are worried about eye tracking, there we are dealing with the stereoscopic perception, that how those two eyes of ours, the evolution gave us two eyes so that we have a stereo vision. And the fact that we have two cameras, two eyes, gives us depth perception in terms of convergence, where our eyes converge, where we are looking at. And then, of course, you can even do this kind of little exercises by yourself after the lecture, that you look at an object and you close your left eye and you keep looking at the same object, and then you suddenly close the right eye and open the left eye. So you see this stereoscopic shift in the environment, and this shift gives us depth information. Of course, this depth information gives us a relationship to the objects and their proximity to each other, and in relation to the distance when you close one eye and open the other eye, how the objects change location. This gives us depth information. But of course, we can use this also for other purposes. For example, foveated rendering. As we talk about the visual acuity of human eye, it's extremely high resolution understanding what we have about the world, but it's a little bit fake because we have only the foveated. If you put your hand in front of you and look at your thumb, the nail of your thumb, that's about the angles, the foveal angles, what you actually see extremely accurately. So with foveated rendering, we can dedicate most of the visual rendering and power to the center of the screen, while we are putting a little bit lower resolution, smaller amount of pixels, for example, with optics to the sides. And also biological psychology is very important for this kind of technical implementation, is that in fovea, whereas the resolution is extremely high, actually the update rate is quite low. So when we move our eyes to an object, it takes maybe 100 milliseconds for us, our brain, to construct understanding what it is looking at. So in the foveal, we need extremely high resolution, but we can a little bit give up in the frame rate. We don't need to update the images as fast. And the opposite is in the peripheral vision, true, that in the side of our field of view, our so to speak, rendering rate is extremely high. We don't see colors, but we are very accurate on detecting motion. And you can explain this also in evolutionary sense, that it's important to be able to see motion in the forest, for example, if you are trying to detect the danger. So eye tracking can be used for also that kind of things, but it gives us this depth perception. And for example, we can do heat map detection. We can do some interactions with the eye tracking. So that's just gaze each of our eyes where they converge. What is the point in 3D space where we are looking at them, and we can use that tracking for many different things. Then the next level, what we discussed, is the head tracking. So we have jumped one layer up, so to speak, from our eyes to the head. And this is what you usually see with different kind of virtual reality headsets, especially the first systems were solely focused on tracking of the head position and orientation, so that within the headset, the rendering is fixed, but just the point of view of your head will be updated based on the head tracking system. And here we are talking about parallax perception. So we have moved from 3D stereoscopic perception to parallax. And to demonstrate this effect, you can close one of your eyes and you still see the world substantially in 3D. You don't need the stereoscopic perception to have a 3D understanding. And this 3D perception comes from the visual cues, visual depth cues, what you have. For example, the fact that you look at an object and the objects behind that move at different speed. So these are the kind of depth cues what you get from the parallax perception. And this same system is used, for example, in simulation. Here on the left top side, you have a MEVEA simulator for Mantsinen loader. And it's important to, if this screen represents a machine window, it's important to be able to render the viewpoint from the perspective of the user's head. And this you can simulate yourself, just go in front of a real window and walk a little bit closer to it, as if you were leaning back or forward in a cabinet. The opening, what you see from the window, is different. And this is the purpose of head tracking in simulators, that you can render correctly. If your screens represent the windows to the real world, you can render the point of view correctly based on head tracking. And then the next level higher is this self-referential perception. For example, if you are using a VR headset and you put your hand in front of you, it's important that you have some kind of tracking system on body tracking level to put your virtual representation of a hand. Unless it's a video see-through or optical see-through, then you obviously see your hand. But body tracking is more about the self-referential perception, that how your body is in respect to the real world. There was a lot of problems with this body tracking combined with the head tracking in the beginning, for example, with Oculus, where you have a lot of drift with the tracking system, that you think that you're looking forward visually. You may have a virtual avatar representing your body, but due to the drift, your head has tilted, for example, 45 degrees. And it's a weird sensation when you take the headset off with this type of a drift, because your brain tells you that you're looking forward, but then you realize that your head is actually tilted sideways on your shoulder, and this muscular sensory feedback is not enough to calibrate. You have to visually be able to see your own body to properly position your head, orientation of your head in respect to your body. So this type of problems, they are not so prominent anymore. Tracking systems are very good, but in the early days of, for example, Oculus, first versions of Oculus, this was pretty big problem. And then the highest level, I would say, like one of the highest levels would be then the location tracking, and it's more about your relative position to the environment and, for example, location. If you think about one of the most classical examples of breakthrough AR was the Pokemon Go. And in fact, the tracking system in Pokemon Go was basically just a GPS and a gravity vector, and everything else you can just fake. You don't really need to know exactly where the objects are. You are able to geolocate yourself in some nearby a park, and without using any of the other lower level tracking modalities, you're just fine. In that use case, the quality and scale of things was appropriate to just use a GPS and IMU to put the content in the right place. That would be the relative perception and systems like GPS and IMU. So we have covered the tracking systems part. So we answered the spatial question where our content is perceived. And remember that to choose the correct level of tracking, that the scale is appropriate to the use case, so that you don't end up having unnecessary complexity in your tracking system. So then we move forward to the display side. We have 4 display groups, kind of main umbrella categories of displays. You have handheld video see-through devices. This is a little bit special group of devices because in handheld video see-through devices, we are just again like kind of tapping into the power of our brain. So in fact, the view to the world is from the point of view of the camera of the device. And our brain, our eyes are just observing the screen where we see the video feed from the real world. But again, our brain is very plastic. It doesn't really care. It's just happily accepting that video feed from the device as if it was itself looking at the real world. And that's why we can, for example, this IKEA style of furniture placement applications just work fine. So our brain just sees that, okay, I get the visual cues. I don't have stereo perception, but I just get enough visual cues to build a mental model how this sofa would look like in my home. So that's the first display group, a little bit special group, but it taps into the plasticity of our brain and adaptability that we can do substantial amount of AR content just with our mobile handheld devices. Second group is hands-free video see-through devices. So they are usually a small hands-free display. In fact, it's the concept, even if it looks like fancy augmented reality, this kind of smart glasses. I like how, for example, RealWear is positioning their device. They are just literally saying that this is a hands-free tablet. So very much the same as our display group 1, where we have a display that we hold in our hand and just look at the point of view. Here we are a little bit closer to the user's point of view. The camera is very close to your eyes if you put the video feed to the display. But in fact, it's just a small little display floating in the periphery of your eye. You are not really observing the world through the display. It just gives you a relatively realistic point of view from your position, your head position to the real world. And you have a tiny little display on the periphery of your field of view that you can render that feed. Additionally, of course, nobody forces you to just use the camera feed. You can use whatever. Remember, if you are using GPS tracking to recognize that the user is in specific factory area or in certain property, you can now provide specific information that is related to that location and just visualized on this hands-free display. So this would be using GPS signal to narrow down the relevant content for this property or for this machine, let's say a rock crusher in a specific open mine, that you get correct information, some diagnostic information from the machine when you are standing next to it. So just be very open with this. How you augment. Is it a concrete augmentation, visual side? Is it the abstract augmentation, just showing diagnostic information from the machine? And what kind of display devices you actually need? If you are doing manual operations, you probably need a hands-free video see-through display, or if you are just observing, maybe just a tablet is enough for you. So display group 3 is wearable optical see-through. So the difference between optical see-through and video see-through is that part of the content is digital and the part of the content is you are literally observing the real physical world. With video see-through, we have a lot more flexibility in our rendering rates and technical requirements. It's fairly easy to render virtual content on top of the video feed, but with the optical see-through displays, it's much more difficult. We start to have a requirement for example, eye tracking, so that we are able to extremely precisely position the virtual content. Again, of course, depends on the use case. And optical see-through, when we look at the real world, it just updates as it is. As we move our head, rotate our head, the real world updates, and usually we have a little bit of a latency in the virtual version and virtual content, and this gives a little bit of a problem in building applications for optical see-through displays. There are not so many on the market, and Epson is probably the widest adopted. It's very good ergonomics. HoloLens from Microsoft is maybe the most popular in terms of R&D and experiments. And then there are some other manufacturers popping up very recently, quite a lot of them. That's the optical see-through version of display groups. And the fourth group is emerging, I think mostly thanks to Varia. So we have very much similar type of displays what we use in virtual reality. But now we actually take two cameras, we position them closely to the same physical location as where human eyes are. And through these virtual eyes of yours, we stream the video feed to the screen. And now we have the wearable video see-through display where we can put content, render content on top of those video feeds from those two cameras. And again, we a little bit win in this situation in the latency requirements because it's easier to synchronize the video feed with the digital content. And again, our brain is just happily accepting. Of course, there are some constraints. If you have a little bit too high latency, you start to get nausea and other things. But let's assume that you achieve those render rates. Video see-through is easier to do technically. But as you can understand, the scope of use cases is usually indoors, R&D laboratories, some review meetings with the designers, and so on and so forth. So that was the display area what we currently have on the market. In terms of content, there are mainly just a lot of content creation platforms. You can use Unity 3D, Unreal Engine. You have some kind of authoring platforms like Vuforia, Wikitude. You have even some more commercial authoring platforms. So there are not so many breakthrough applications in AR. And I would claim that part of this lack of applications is the fundamental misunderstanding of the role of the technology itself, and the part one what we went through and understanding like what is it at the end of the day that we are trying to achieve with augmented reality. So on that content side, it's still pretty weak. We haven't got our breakthrough AR applications, not so many of them. So part two, we have completed. How does AR look today? We have the tracking, answers the question where. We have the displays on how we visualize the content or augmented real world. And then we have the content about the use case. What do we want to augment and why? What is our goal for our augmentation? Plenty of room there on the content. Hopefully you will be also participating on solving that content question and figuring out interesting ways how we can enhance the human capabilities with AR rather than just hunting Pokemons. We're almost done, in fact, because one very big aspect that we are completely skipping today is interaction metaphors. So we have been mostly focusing on how we perceive the world. What are the sensory inputs that we get to make conclusions and to build our mental models about the world. But the output side, how do we actually interact and manipulate our AR content or virtual reality, what we would call interaction metaphors. We have voice commands, we can have gesture controls, we have mouse, we have keyboard on our computers, we can have trackpads, we can have touchscreens. So this interaction metaphors is actually a substantial problem, a big problem that nobody has really addressed very well yet. For example, I can give an example if we go a little bit back and look at this category of display group 2. RealWear has decided that their system is only interacted with voice commands without any kind of a trackpad, only voice commands. And you can understand that only having voice commands is almost like using your computer with just command line interface. I know the Linux guys would love to have their computers only with command line, but you can argue that there are advantages that can be gained when you actually have instead of command line instructions like voice commands, open application this and that, close menu, do this, do that in the command line way, that you can actually use the mouse cursor or touch screen or gesture controls to manipulate things. So this is a big problem still with AR and VR, that is having a good set of interaction metaphors is still substantially missing. I was planning to publish a blog post on that. I'm not done with it yet, but feel free to follow me on LinkedIn, and I will work on it and make kind of a state of the art review on that one. So interaction metaphors are problematic still on all the VR and AR systems. So we can go to the part 3. Where are we heading towards? What will the future look like? And in this, I will give our story of our company. I like the fact that you already got inspired by the part 1 and your imagination started go wild on all the opportunities that we actually have. And there are plenty of opportunities, and we're just barely scratching the surface. So I think I leave a lot of it for your imagination, and I will just go through our journey and what we are trying to at Delta Signal Labs, what we are trying to do with augmented reality. So when we were researchers at VTT, we had this notion we are human machine systems, and we are concerned about the human ability to understand things. And one concept was that popped up through a Japanese scientist Nonaka in organizational knowledge creation, and there's a concept of explicit knowledge. For example, when you're able to write a manual, instruction manual, let's say for an IKEA furniture or a tractor, how to operate, this is called explicit knowledge. This is just informational content, rules and procedures, and that type of information is rather easy to save into a database or put into a Word document and distribute. But far more challenging form of knowledge is tacit knowledge, this kind of silent, practical knowledge that, for example, a maintenance engineer has. I don't know if the modern kids do they even know MacGyver or Star Trek, but on the top picture you have an example of data playing poker and completely playing on statistical premise, and on the bottom you have a MacGyver trying to solve some problem with whatever means he has available. And I felt that that's a fairly good representation of difference between explicit knowledge, numbers, pure information content, and this kind of practical knowledge what for example, service engineers on the field dealing with machines, what they have. For example, in some of our review meetings with designers, when we brought some technicians to explain how certain maintenance tasks should be done, we found that virtual reality, in fact, was the only way that they were able to articulate and communicate about the tacit knowledge. They are incapable, some people literally, but at least metaphorically, they are incapable of articulating and explaining their knowledge about the service of machines in an explicit way, write it on a piece of paper. But when you put them into a virtual environment, they are able to show by example that, hey, this is how I would remove the wear parts on this rock crusher. I would go like this, I would take a look from this angle, I would remove these bolts like this, and I would check the wear here and so on. So this is the tacit knowledge, and this is very difficult to capture and specifically store. So we realized that, okay, especially in the context of space industry, I will explain a little bit about that maybe augmented reality is actually helpful in communicating tacit knowledge. That a lot of times the technical people are able to operate tools, measure voltages, use this different kind of technical operations, but what they don't know is in what order to do it, how to interpret the results, and that's from where our AR collaboration tool came from. It was the idea that let's try to use augmented reality in helping remotely to communicate tacit knowledge, what to do next, how should I open this, and that's what we started to do. And for us, the initial problem was pretty obvious. We were contacted by Thales Alenia Space, and astronauts have these sleeve checklists where they have most of the basic instructions, procedural sequences, and they ask, like, guys, like, do we have any better technology to handle these complex maintenance scenarios that we wouldn't need to rely only on this kind of explicit knowledge based instruction sheets. And we were thinking that, okay, we could try to use AR. And in fact, when the ground control is trying to support the astronauts, they have video feed, they see what is going on. But sometimes it may be difficult to even say verbally that, hey, can you check this bolt above or left? Because the astronaut could be in fact upside down. There's no up and down in space because you don't have gravity there to align everybody in the same direction. So verbal communication and collaboration is actually difficult. But that's where augmented reality can step in, that you see the video feed and you have a feedback channel back through augmentations, as if you were already there with the astronaut fixing the things and pointing with your finger that, hey, can you open that bolt? Can you check voltage from this pin? And that's what we started to do. We started with hardware product. Idea was that we use projected augmented reality, and it was fascinating at the time because when we were doing the first prototypes of Astrovar device, of course, these hardware products, it was just about the time when Nokia was collapsing in the hardware side, so it was very difficult to raise capital for hardware products. So and of course, like projecting, you have the light emission problems and others. So we thought that, okay, let's think it over and pivot from the hardware product. Let's use the same AR concept. It feels like this is super powerful concept, and let's try to think that what is essential in this. What is the essential aspect of our system? That, okay, we have this kind of a scenery. We see the video feed. We are trying to classically explain with the verbal commands that, okay, could you check this bolt or that bolt? And if in fact only thing that we want to spatially, we want to give a feedback channel to spatially help the people interacting and solving, debugging some complex problem, that maybe if this AR, maybe we don't need the hardware at all. Maybe this project augmented reality, it has advantages. It's multi-user. It's nothing on your face, so it's a beautiful concept. But if it's just distilled down to the essentials of AR, maybe we can just turn it into a mobile application, and that's where our current product Pointer emerged. So we simplified the hardware configuration, just adopted the same software, and put it on the mobile devices so that anybody can use and remotely instruct other people to perform technical tasks. So we bring communication beyond voice and video. We introduce the feedback channel of remote instructions through augmented reality. And as we started with collaboration, we have been now starting to go more to the horizontal directions and actually cover all of the industrial process phases, that whenever you are collecting information for your sales, pre-study from the customer side, actually it's very helpful where you can use augmented reality to annotate, measure distances, collect data for the designers. And then when the designers are starting to, for example, make 3D models of the new system, let's say you're designing hangar doors or installing, retrofitting a new exhaust system to an old device, the designers sometimes need to check their initial requirements that everything is correct, and they can use the same tool to call the customer and have a real-time feed and to document the situation. And then in design reviews, distributed design reviews, when you're actually procuring parts, quality control, once you deliver your systems, you can document the delivery, and once the customer adopts your product, you can give remote guidance to help them to use the system. And at the end of the day, when you do the billing, reporting, and you can sell services. So, and of course, throughout the whole time, you are doing quality documentation, quality reporting. So that's our way of bringing spatial reasoning and enhancing human abilities in collaboration and industrial project delivery, and that product is Pointer. So this is how we are trying to adopt these lessons and bring business value from AR. So just to recap, the purpose of AR is augmenting the human capabilities. It's not about the smart glasses, it's not about the tracking technologies, it's not about the fancy rendering. We're trying to augment the human. It's fundamentally human capabilities that we're trying to augment in unity with the best of technologies. So in full unity, neither of these aspects, society or technology, are the primary, but together they form a human machine system that takes us beyond our biological limitations for the purpose of achieving our use case goals. So now I think the question is more that where will you take us with AR with these lessons? I leave it to you, and I thank you for your attention.
Very good.
At this point, any questions?
I have actually a question about this Lundberg lens control. How does it work that you can translate image through taste?
So it will be easier to explain if I think about, and I explain from our point of view of our fingers and how we sense touch. Let's take a look at this Yuta Takeuchi and example. So they made a system that they use a microphone in the hand in the green carpet here. This is just a microphone, and they move that microphone by touching on the surface. So this records a very, very accurate wave, pressure waves from the touch sensation. And then they are able to transmit these waves and play it back with the actuator on the finger of the user. And it's extremely, I have been able to test this system myself. It's extremely strange sensation when they are able to play back these waveforms, and your brain goes and says that, okay, now I feel a fabric. Now I feel something metallic. So this gives an idea about our sensory capabilities, that if you look at the human fingertip, how sensitive it is. We know about visual acuity, like how good resolution our eye has, how well we are able to observe the real world. We have the fovea, we have the peripheral vision, and how good visual perception of the real world we have, but we don't have so good understanding about our other sensory capabilities. And fingertip is a good example of this, because if you think about fingertip and you try to imagine it scaled up to the size of planet Earth, scale it up in your imagination to the scale of a planet Earth, your fingertip is able to sense as small objects and changes in the surface properties as a car or a house on the surface of the Earth. So this gives us some kind of a like scale, how big bandwidth we actually have on our fingertip that is completely unutilized. So if you think about our aural capabilities, through evolution, we are able to produce pressure waves. The same kind of a bandwidth is available for communicating as an input channel through our fingertips. And if you think about output, we type things on the keyboard. It's pretty low bandwidth output, but as an input, a sensory input, fingertip is extremely high bandwidth, and we haven't explored that yet very far. How could we actually tap into this another channel if we are sensory overload in terms of in our visual sense, and we have aural signals, beeping, we have some warning signals, like we have more channels that we could utilize without exhausting our sensory. So in the same way, what they did with the Lance Corporal Lundberg, they just take the low resolution image of the camera and this electrode plate that he puts into his mouth, it's actually producing small electrical signals in the different areas of his tongue. And the brain quickly develops ability to recognize different electrical signals and actually form perception, mental image of what is being shown in the visual sense. So for example, in the right side, he's able to recognize the text cat. So not only physical objects and distances to objects in visual sense, but also in abstract reasoning, he's able to recognize letters only through the taste, how the world, he's tasting how the world looks like. So this is the thing about the sensory input and the channels that we have, that in this scenario, they are just a little bit pushing the boundaries and seeing that what kind of bandwidth we have in our taste system. Was that a good overall explanation and covered your question?
Yeah, that was a very good explanation. Thank you. And that's quite amazing, actually. It's like when I think about it, it gives so many possibilities, like it's almost limitless.
Precisely. When we look at this picture of the gentleman with his graphics representing some stock market changes, or the gentleman on the right concerning about how can he have all the time to read all the books. It looks very demoralizing that we have reached the end of our capabilities. There's just too much information. But in fact, when we look creatively about these examples, we realize that, I think there's still plenty of ways to go. Whatever evolution has given us may not be necessarily the most optimal way that in the current advent of technology, that how we can actually input information into our brains.
That's exactly what I was thinking when you were showing this time scale of evolution, that because we are now here, but we are not there yet. There is still evolution ahead of us. So, like you said, we don't feel, well, most of the magnetic field spectra and stuff
Indeed.
like that. And birds, for example, seem to feel it. Like that's why they
Exactly.
totally migrate. So I was
Exactly.
thinking, what will happen? How will we see the world in 10,000 years?
Precisely. I love this bird example. Like the more we are finding about this, how different animals through evolution have ended up in solving, for example, navigation problem. And there was this strong sense of forcing our understanding of the world that it must comply how humans have evolved. And now there's more and more acceptance to the fact that no, in fact, there is different ways, and evolution has figured out different ways to solve the navigation problem. And in your example, it's a great example how it works with the birds and their ability to sense the magnetic fields of the Earth. So that's a good example.
One thing about the plasticity of the brain, I started thinking about that in this Lance Corporal's case, he has lost his vision.
Mm-hmm.
So the area of the brain where he usually processed visual data was now freed for other tasks.
Indeed.
And I was thinking that when we get more of this kind of augmented reality things into our lives, what will they replace if we don't does human brain has extra capacity to handle lots of new inputs, or will it replace something?
I think there's plenty of room for still, like our brain is like a super low power supercomputer. And I think there's still plenty of room for new things. But I think out of necessity or out of obsolescence, some areas will actually disappear and literally give room, as you described, give room for the new ways of perceiving and understanding the world. If you think about, for example, telephones, back the days it was very important for us to remember numbers, certain length of sequence of numbers, because we had to remember the phone numbers of the neighbors, of the parents, and so on. And actually today it's kind of almost obsolete characteristic to learn. So I think like naturally that kind of characteristics that were very important a while ago will go away, and hopefully we will find one would hope that we find new ways to utilize this brain capacity of ours and use it for good and improvement of humankind, instead of it just being an empty piece of land. So
Yes, exactly. And I think that's in the whole scheme of education. We have moved away from memorization and more into utilizing the information rather than we test that if students can remember this and this many things.
Indeed.
But one thing about the plasticity, I was last week I was building this virtual factory demo for the students that we will go do tomorrow. And I have to say that when I was working for a week in that environment, I started kind of feeling a little bit out of this world, I would say. When I lost the virtual gear and went home, I kind of still felt that I'm in some kind of virtual reality, that my brain adapted to that already so well that it was really difficult to kind of come back to the reality.
I think that's like that kind of consequences, hopefully not so much negative consequences, and but I think it's probably like what we had the problem with the cars, that before the speeds that humans were able to travel the world was on the range of few kilometers per hour, and the idea that humans can travel, for example, at at 60 kilometers per hour, 100 kilometers, at that moment for people that felt completely absurd, that this is never going to happen, that we cannot, our brain is not able to comprehend that kind of speeds. And slowly and surely we just did it. There's no problem. Our brain is just able to observe the fast moving objects and acknowledging our limitations in the number of objects that we can recognize. It's about 4, I think, that we shouldn't be texting while driving. Once we respect those limitations, we are still safely able to go in the traffic. So I would hope that this kind of effect happens also with the phenomenon you described, that in the beginning we feel these transitions from the real to virtual slightly awkward, but hopefully in the future we just adapt to it, and our brain as in the example of the wheelchair, at the end of the day the subconscious brain doesn't really care what's going on. Like for example, these examples of using glasses that flip your field of view upside down, and just in matter of few days your brain actually accepts this as a fair input, that doesn't care. It's just like, yes, the world is upside down, but let's go, rock and roll, no problem. So I think the plasticity will just help us there, that we will not have negative consequences.
Thank you again. Really interesting lecture in total.
Thank you for your attention.